Good evening, everyone. Good evening. Good evening, everyone. Welcome to Unacademy, India's largest online learning platform. Good evening, Vinod. Just waiting for a few more students to join. Okay, before starting, good evening, Vasu. Vasu, hope your problem is solved. I think you can download all the notes of my classes from the Telegram channel. I don't know whether you got it or not. Hope you got my notes. Hope you got the all classes notes till now. That's great. That's great. Okay. Okay. Coming to today's class. This is the electronic devices subject, which is very much useful for EC students, and a few parts of EE and instrumentation should people should also have some idea of this subject, right? So this is for GATE and ESE also. GATE and ESE. Right. This is going to be lecture number 13. So introduction to PN Junction Diode. So far what we discussed is semiconductor physics. This is the second part of the most important EDC. EDC. So sometimes you may get 13 to 14 marks also. Sometimes a minimum of you will get 10 marks. Minimum of 10 marks you will get from the subject, sir. Minimum of 10 marks you will get from the subject. Okay. Yeah. So myself, Shravan Kumar, having master's degree from JNTUH in VLSI system design. I have 10 years of teaching experience, and subjects which I have taken is EDC, analog electronics, digital electronics, EMFT, digital electronics and EMFT. So I have a promo code, that is SVS10, to get 10+% of Unacademy plus subscription. Unacademy plus subscription. Okay. So what is the use of having plus subscription? What is the use of having plus subscription? A plus subscription student will get live classes, and he will be there. He will be using crash courses. And this is the most important thing, which I always stress, sir. GATE is not just about listening and reading. So it's all about testing yourself. Every week you will have a test. The plus student will have an advantage of weekly test. The plus student will have an advantage of weekly test. And you should see the most important thing is this is also doubt solving sessions. Doubt solving session. We'll have a doubt solving session, sir. And the teaching will be in English and Hindi. Hindi for North Belt students, it will be very much useful, and South students and other non-Hindi students can listen to the classes in English. And we have something called rank improvement batch. For those who already got some good rank and looking to improve their rank, this is called rank improvement batch. Okay, so these are the advantages of having plus subscription. If you go for iconic subscription, the best part is you'll have a personal coach. You'll have, every individual will have a personal coach, and who will guide you completely from one end to end. And you have a customized study plan. So he will ensure that where you have to learn which subject and everything. He will definitely see. You'll have a study planner, and you'll have something called study booster sessions. So essential guidelines and workshops. So how to improve your concentration, how to improve your subject, everything will be given here. And you'll have something called personalized test analysis. After every test, they will give you detailed analysis in which subject you are weak, in which area you are weak, in which subject, which area you are weak, everything. How did you write the exam? This is also very important. This is like a feedback. This is like a feedback for you. So every feedback is very much important, and you will have a specialized notes. This is very much useful, sir. Right? So these are the advantages of having plus and iconic subscriptions. So the plus subscription for 12 months it is going to be 27,225 rupees. And if you want to get the 10% discount, you can use this code called SVS10. 10% discount. For 18 months, it is going to be 34,650. 34,650. For 24 months, it is going to be 39,600. It is going to be 39,600. It is going to be 39,600. Good evening, Pritam. Welcome. Yeah. For iconic, it is for 12 months. You are going to have 45,225 rupees. 45,225 rupees. And you will have a SVS10 is my code. SVS10 is my code. And for iconic batch, you are going to have something called 66,600. That is SVS10. SVS10 is promo code. So you can pay all these things through EMIs. You have EMI, you have wallets, you have different wallets you have, and you can use a credit card. You can use credit card and debit card. So there are different ways to pay all these things and pay and join for these courses. And this is a Know Your Basics is targeting for GATE 2022-2023, which are the free classes. So free classes will have a disadvantage. They don't conduct any test kind of thing. You can just listen to the classes. But the best faculty top educators will guide you. You'll get the guidance from the top educators, and you'll have introduction across all the subjects, across all the branches, right? So a complete roadmap to approach each of the subject of every branch. Okay, this is very important. In targeting 2022-2023 and subject-wise strategy, which subject need to be how we need to study which subject. Everything will be discussed. Right? And this is for this already started in yesterday only. So this is for a mechanical, civil, EEE, ECE, CSCIT, and chemical engineering. For everybody, you will have this. Everybody will have this. And next, so this is something called Ascent. Very important, sir. This started today. Only. Today only. You have still time. Something called Ascent 2023. Those who are targeting for 2023, this is the best time to start. You have almost 2023 means you have very good time. Those who are in third year, almost 2.5 years, almost two years. You have 2 years of time is sufficient to get all India rank, all India good rank. Maybe below 100 also possible. If you are starting, if you are in second year or third year, this is so even if you study very well, you'll get Air India below 10. AIR 1 also your target. If your AR1 is also your target, you can go for this. You can go for this. These the batches will be in English and Hindi, as I told you earlier. So for the ECE, you can use this promo code ECE GATE 10. These are the top educators of Unacademy. These are the top educators of Unacademy who will teach you from the basics. And this is assigned GATE 2023 for electrical branch. As I told you, same. This is also started today. This is also started today. This is also started today. It is in English and Hindi. English and Hindi. This is the top educators of our Unacademy, and you can use this promo code EE E10, EE 10, EE Gate 10 is a promo code for 2023, sir. 2023, and you have for 2022 also you have for 2022 also you have for 2022 also you have English and Hindi. So which also started today, and that is name is Evolve. That is name is Evolve batch. So top educators will teach you, and you have again ECE Gate 10, ECE Gate 10 as a good evening Balaji. Good evening, good evening. So good evening. So ECE Gate 10 is what the promo code, right, for Evolve. Right. This is for electrical engineering. Same WE Gate 10. Again, top educators will be there to guide you from the scratch. So this also started today. So teaching will be in English and Hindi. This is targeting 2022. 2022 is the target. 2022 is target for Evolve. For Evolve, it is 2022. For Ascend, it is 2023. Okay. Yeah. Now, those who want to follow me, you can follow me. I request you to all follow me on Unacademy. At Unacademy, user is Z6 I4A9 LLPDQQ. So it is already there in my notes. You can download it from my notes. Not clear? Yeah. So this is what PN Junction. Before just going to PN Junction, let's recap what we discussed in the previous class, as we do it every day. So I think we discussed some problem, starting with some problem. 2, 3, I think four problems we have discussed, and we have discussed something called Hall effect, which is very much important. Which are the last topics of the semiconductor physics. Last topics of the semiconductor physics which we have discussed. So Hall effect. What Hall effect says, sir? When a specimen carrying a conductor I, carrying a current I, is placed in a transverse magnetic field, it it induces a electric field. It induces electric field E, and which is called Hall effect, which is perpendicular to both I and B. Is perpendicular to both I and E. And this phenomenon is called Hall effect. Why? What is the importance of Hall effect? Is whether the given semiconductor is N type or P type. So to find whether the given semiconductor is N type or P type, this is very much important. Hall effect will explain you how to do it. Hall effect will explain you how to do it. And you will also have something called finding carrier concentration. So you can also find a carrier concentration. You can also find the carrier concentration using this Hall effect. And then you can calculate mobility by measuring conductivity. This is a very important thing about Hall effect. And we discussed how Hall effect helps us. This is the Hall voltage. This is the Hall voltage. This is very much important. VH is equal to BI by rho W. And this is a Hall coefficient RH, which is 1 by rho, VH into W by BI. So and this is how you will measure. This is how you will measure mu mobility by knowing conductivity. If you know the conductivity, you can calculate the mobility. So this is how Hall effect is important. Importance Hall effect, that's what we discussed. I need not mention it again. And we have discussed something called generation recombination of charges. As thermal agitation, due to thermal agitation, electron and hole pairs are generated. And at the same time, parallelly they will disappear. So some new electron hole pairs are forming. Some of them are old or disappearing. Balaji, yes, we will finish it off all the lessons. Yeah. Good. Ask some of your friends also to follow. Ask some of your friends to follow this. It will help you a lot. In which year you are now? Which year studying? Balaji, which year you are studying? I mean to say, for which year you are targeting GATE? Okay. So the new electron hole pair will disappear after some point of time. The time taken by the charge carrier now in second year. Good, very good, Balaji. You are very lucky. You are very lucky. You have ample of time. You have ample of time. Yes, definitely you will complete all the subjects. Yes, definitely you will complete all the complete subject. You can crack gate before your in your fourth year itself. You can crack your gate. In fourth year itself, you can crack your gate if you follow with this pace. But the only thing is, as I told you, not reading and listening to the classes is not sufficient. You have to practice the problems. So we will in due course of time we'll make you to practice as many problems as possible. Good that you are attending the classes. Good that you are attending the classes. Right? This is extraordinary. Wish you all the best. I wish you all the best. Very good. Okay. Generation recombination of charges. Generation recombination of charges. So as I told you, this is the tau p is a mean lifetime of hole or mean lifetime of the electron. Tau n is called. So the generated electron will disappear after some point of time. That time is nothing but this one. So this is what we discussed in detail. In carrier lifetime, what I was discussing about, and we have derived generation recombination dp by dt. This is for n and p naught and p. We discussed in detail. Those who missed my class, they can go back and listen. Those who missed my class, they can go back and listen. So continuity equation, very beautiful, sir. Very important continuity equation. What is a continuity equation? As we know, the carrier concentration changes with respect to distance and time. The partial differential equation which governs the functional relationship between carrier concentration, distance, and time is nothing but continuity equation. So how the carriers are changing with respect to time and distance will be defined by the continuity equation. Very important, very important. So this is a derivation which we have done. In detail we have discussed in the class. So these are the two continuity equations for holes in n-type, continuity equation for electrons in p-type. Sir, remember continuity equation is important. These are the minority charge carriers. Minority charge carriers. Minority charge carriers in n-type. So I in detail we have discussed about why minority charge carriers increase or decrease is important, right? So go back and listen to the previous class. All of you, those who missed my class, I would request all of you to go back and listen to the class. You'll definitely understand very clearly what is the purpose of this continuity equation. Continuity equation. Okay. And we also discuss something called diffusion length. Diffusion length, we can call something called length of diffusion also we can call length of diffusion, which is equal to square root of d by t. D is nothing but diffusion coefficient. Diffusion coefficient. That diffusion coefficient can be calculated from Einstein relationship. Einstein relationship. From Einstein relationship, we can calculate d. If you can be able to calculate d, you can calculate the length of diffusion. How much length it is penetrating? How much length it of almost no. This is the new topic. This is the new topic. You will understand. PN junction diode. Of course, there is an interrelationship between what we discussed in semiconductor physics and PN junction diode, Balaji. But still, you just follow the class now. So I will ensure that you will understand what we discussed, right? So, but still, for clear clarity of the subject, I would request you to go back and listen. Not now, later on, right? Today you just flow with the class what we are discussing. Clear? Clear? Need not worry. Need not worry. So this is what we have discussed. This is what we discussed in the previous class, I think. Yes. So coming to the today's class. Yeah. Today's class is about a PN junction. A PN junction. You understand it very clearly. If donor impurities are introduced into one side, and acceptor impurities are on the other side of a single crystal semiconductor, a PN junction is formed. Is talking about this junction. Don't think that a p-type material, a p-type and then another n-type as brought together, that forms a PN junction. This is a p-type, this is n-type. No, we will consider a single crystal. We'll consider single crystal. Let's consider this pen as a single crystal. What I'm talking about. So on one side, you will pour donor impurities. What do you mean by donor impurities? All pentavalent atoms. These are pentavalent atoms. So what is acceptor impurities? Acceptor impurities are trivalent. Acceptor impurities are trivalent. Okay. So on one side of the given semiconductor crystal, you will pour donor impurities. On the other side, what happens, sir? You will pour a acceptor impurities. Now, what happens, sir? At this point, at the center, there exists something called junction. So, what do you mean by junction in general? So, which will divert from one place to other place generally, right? So, now what happens, sir? In this, if you are, let's say this part is you are pouring with acceptors, and in this region you are pouring with donors. So now this complete n-type consists of donors and complete p-type consists of acceptors. Now when you are trying to move from this end to this end, so after crossing this point, you will be entering into something called n-type. Till here, what you are, sir? You are in p-type. So after crossing this line, you will be entering into n-type material. So that is why it is called junction. This is called junction. So as this is formed in between p-type and n-type, it is called PN junction. It is called PN junction. Is that clear? So why it is called PN junction? Because the junction is formed in between p-type material and n-type material in a single crystal. Okay, next. Now the donor ion is indicated schematically by a positive sign, because after this impurity atoms donate an electron, it becomes a positive ion. So what is saying, sir? Is saying a donor is represented with a positive ion. A positive ion means a donor. A negative ion means a acceptor. So I have already previously discussed why this is represented with positive and why that represented with negative. Why donor is represented with positive? Why acceptor is represented with negative? I'll again explain you. Here. Simply, let's consider silicon. So what is silicon atomic number? Atomic number 14. So what do you mean by 14 atomic number means? You will have 14 electrons, and see this completely, how many electrons are there? completely. You have 14 electrons originally. 14 electrons. At the center, at the nucleus, you have 14 protons and 14 neutrons. Let's say one electron is donated. One electron is donated. One electron is donated. When one electron is donated, so what happens, sir? In the center, you will have 14 positive charges. You will have 14 positive charges. Now, in the circular orbit, how many electrons you have? Only 13 electrons you have. Only 13 electrons you have. It means now which are higher? You have 14 neutrons. 14 neutrons. You have 14 neutrons and 13 electrons. You have 14 neutrons and 13 electrons. Which one is higher? Which one is higher? So what you'll get is +1. So this plus, that is the reason why we call this as a positive ion. Positive ion. By donating an electron, any atom will become positive ion. Any atom will become positive ion. Okay, any atom will become positive ion. Right? So similarly, if it is accepting one electron, let's say what happens here? You will have, let's say the silicon has accepted one electron, example I'm telling you. So 14 neutrons we have. So how many electrons will come? 15 electrons. So one electron is added. Let's say one electron is added. So you'll have 15 electrons. So you have 14 neutrons and 15 electrons. So what you'll have, sir? -1. -1. So this minus is nothing but acceptor. So on this it becomes minus ion. Minus ion. This is becoming minus ion. This is becoming minus ion. So by donating one electron, it becomes a positive ion. By accepting an electron, it becomes a negative ion. Hope the point is clear. Hope the point is very clear. Yes or no? Hope the point is clear. Okay, next. So initially there are, see that I just wanted to show you this. So now you can see here, these are all donor atoms. Sorry, these are all positive ions. Positive ions. And these are all negative ions. These are all negative ions. Why these are positive ions, sir? Because this can give you one electron for conduction. This is accepting one electron. This is accepting one electron. Because of that, it's called negative ion. Ions. Hope the point is very clear. Hope the point is very clear. If you have any doubt, let me know immediately. Let me know immediately. So, do you want me to move on? Okay, let's move on. Let's move on. So initially there are nominally only p-type carriers to the left of the junction and only n-type carriers to the right. Yes. 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 Okay. Because there is a density gradient across the junction, holes will diffuse to the right across the junction and electrons to the left. Due to diffusion, some of the holes from p region enter to the n region. They find number of donor atoms. So what he's trying to say here is, I'll just try to explain you in detail. I'll try to explain you in detail. As I told you, this is a P region. This is P region. This is N region. Now let us say I have negative ions here, which has holes, 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 holes. You have holes. You have holes. You have. Be patient. Learn everything slowly. Slow and steady wins the race. If you want to run fastly, you can't make it anything. So don't think that I'm teaching very slowly, because I want all of you to understand everything. I want to all of you to understand everything. So see, what I'm trying to do is I'm trying to draw the PN junction. PN junction. So here what's happening here? So what the statement says is, on one side we have holes, on the other side we have electrons. On the one side we have holes, on the other side we have electrons. These positive are nothing but positive ions, and these are nothing but negative ions. See, at the junction, now what happens, sir? This hole will try to find its relationship electron, or this electron may move from here to here. This may move from here to here. This electron may move from here. So the holes near the junction may jump to the N region, or electrons in the near the junction may jump into the P region. Now what happens, sir? When an electron is trying to cross and fall into the yeah, and trying to fall into the, oh, 1 minute, just a second. So I'm trying to fall itself into the hole. Now when electron hole is recombined, then where is the point of ion? Where is the point of ion? Ion will disappear here. This extra electron is disappear, and this extra electron is disappear. Extra hole disappears here. So that is what it's trying to say. So there exists a density gradient. On one, what do you mean by density gradient? On one side you have maximum holes, on the other side you have maximum electrons. So definitely there is a density difference. There is a definitely. So complete holes here, complete electrons here. So what they try to do, sir? The holes in one side will try to get into the N region, and the electrons in one region will try to get into the other region. So when they come together, the electron hole recombination will happen. Electron hole recombination will happen. So that's what is due to the diffusion. That process of moving, charge carriers without any external voltage, nothing but diffusion. The process of movement of the charge carriers without any electrons in a given semiconductor is nothing but diffusion. Right? So due to this diffusion, the holes from P region enter into N region. They find the number of donor atoms. Now the holes recombine. That's what I'm saying. The holes recombine with the donor atoms. As donor accepts additional holes, they become positively charged immobile ions. Now the charge is same. The charge will not change, but they have become immobile. The ions cannot move. Because they got the electron holes. The electron hole recombination has happened. When electron hole recombination happens, they'll become immobile. They cannot walk. They will become immobile ions. So this happens immediately when holes across the junction ends across junction, and the number of positively charged immobile ions get formed near the junction of N type. N type. So atoms on p side are acceptor atoms. The electrons diffusing from N side to p side recombine with the acceptor atoms on p side. As acceptor atoms accept the additional electrons, they become negatively charged immobile ions. Now, as I told you in the other case, the p regions, the electrons. I'm talking about this. So this I'm talking about this. So when this electron moving here, this becomes immobile ion. This immobile ion. This becomes immobile ion, and this also, this whole when it is moving from this junction, this also becomes, this negative ion also becomes immobile. Immobile. No. So such large number of negative charge immobile ions get formed near the junction on the p side. So you can see here. You can see here very clearly. I have mentioned here. Very clearly I have mentioned here. Very clearly I have mentioned here. See it properly, sir. See it properly. Do we have extra positive charge here? No. Extra electron charge here. So because of this, this is called. So this, in this region, no mobile atoms, or I can say these are all immobile atoms. Immobile atoms. So once these immobile atoms are formed, now what happens, sir? This is becomes like a block for the other electrons and holes to move from this region to this region. This region to this region. So now what happens, sir? Now this has become like a wall. This has become like a wall. So these are all immobile atoms. So this region is called depletion. This region is called depletion region. So why this is, sir? This is depleted of the charge carriers. Depletion region. Depletion region. This is called depletion region, where you will have only immobile ions. Only you will have immobile ions. Only you will have immobile ions. Very important, sir. Very important, sir. Or you can also call this contain uncovered charges. Uncovered charges. Uncovered charges. You can call this a depletion region. You can also call depletion region can also be called as depletion region can also be called depletion region. Other name for depletion region, sir. Depletion region is also called space charge region. Space charge region. Other names are this is other name region. You can also call transition region. Transition region. You can call this as a transition region. You can call it as a transition region. Transition region. Okay. Now, so the open circuited PN junction diode, which we are talking now, we'll continue our discussion in detail about this. So what do you mean by open circuited open circuited PN junction diode? PN junction, not diode. Diode concept will come to later. First, we'll discuss about open circuited PN junction. I'm just trying to explain you in detail, sir. Need not worry. I'm here. I'm here to tell you everything. Have patience. Have patience, but don't forget to don't forget to like and share. Yeah, correct, Vasu. Potential barrier. We will discuss about the potential barrier. Next discussion will be on that. Next discussion will be on that only. You need not worry. So we will discuss the same thing. I'm just trying to redraw it so that you will have a good understanding of this. Every point is important. As I told you, so these are all plus. These are all on P side. Assume that is going to be P side. This is going to be N side. So what you will have, sir? You will have a positive ions, positive ions, positive ions with the free electrons here, the free electrons here, free electrons here, and this is all negative ions. You'll have all negative ions, all negative ions here with the holes. You'll have with the holes. You'll have because it is a P type. What are the majority charge carriers in P type, sir? The majority charge carriers in P type are holes, whereas the majority charge carriers in N type are electrons. Whereas the majority charge carriers are electrons. Electrons. So this region is called depletion region. Depletion region. So assume that this x is equal to 0 here. So this point is, let's say, xn naught, xn, this distance, and this point is called xp naught. And this is when you are moving away from the junction. So I'm calling this as a minus xp naught, minus xp naught, minus xp naught. What does it mean by xn naught and xp naught, sir? Xn naught is penetration into n side, and whereas xp naught is penetration into p side, penetration into p side. Is that clear? So now here very important thing to be remembered here. Now what happens, sir? Here all positive ions are existing, that is the immobile ions. All negative ions are existing here. Now what happens, you can see it is simply looks like there exists a electric field. There exists a electric field. At this xp naught, all the positive holes are accumulated, and here all the negative holes are accumulated. So electric field exists because of these two. Electric field exists because of these two immobile ions. These two immobile ions from xn naught to xp naught. So what will be the direction of electric field? What would the direction of electric field? Electric field direction will be electric field direction will be in this direction. Electric field. Why in this direction, sir? Why in this direction? So if you bring one positive charge here and place it here, it will be moved away from here. Because of repulsion. If you bring an electron here, it will move away from here because of the repulsion. So remember, electric field is in this direction. Electric field in this direction. Electric field is in direction, right? So as I told you, there exists some movement of charge carriers. When the movement of charge carriers exists, I can say there exists a current. In an open circuited PN junction, the electric field is existing. The electric field is existing here. Now, because of that, some electrons will moving. Electrons and charge carriers are moving from one region to other region. Sir, when charge carriers are moving from one region to other region, what we can say? There exists a current. There exists a current. There exists a current. And this current is nothing but what? This current is nothing but diffusion current. This current is nothing but there exists a diffusion current. Diffusion current exists because of the diffusion current. Diffusion current exists because of concentration gradient. Concentration gradient. Concentration gradient. So what is J diffusion? Let's consider current density. So J diffusion is because of JP diffusion. What do you mean by JP diffusion, sir? What do you mean by JP diffusion? JP diffusion is nothing but the positive charges, right? That means holes. When holes are moving from this region to this region, holes are moving from this region to this region. So this J diffusion will be in this direction. So this is, I can call JP diffusion, right? Now electrons are moving in this direction. Electrons are moving in this direction. So holes are moving in this direction. Holes are moving in this direction. So because of that, we will have diffusion current density in this direction from left to right. From left to right. Correct. Correct. Then electrons are moving in this direction. Electrons are moving in this direction. Yes or no? From P to N. From P to N. This is from N to P. So N to P. So from N to P. From N to P when it is moving. So what is its direction of the current? Current will be opposite. So that is, I can say JN diffusion. JN diffusion. JN diffusion. So the diffusion current is nothing but JP diffusion plus JN diffusion. JN diffusion. JP diffusion and JN diffusion. JP diffusion, JN diffusion. So, and now you can see this distance is called potential barrier distance. Potential barrier distance. So which is equal to, the W is equal to the summation of xn naught plus xp naught. So this is length of diffusion, this is a depletion layer width. Depletion layer width, which is very important. We will have discussion in detailed discussion on this. We will have a detailed discussion on W, that is xn naught plus xp naught. This is very important. This plays a major role in calculating VT. We will discuss in detail. Okay. So it is J diffusion is equal to JP diffusion plus JN diffusion. But another important thing here. So what are the charge carriers here? Holes. These holes are attracted by the electrons here. These holes are attracted by the electrons here. These holes are electrons. So because of this electric field, because of the internal electric field because of electric field existing, electric field E, because of electric field E. So the electrons will be there here or not? Minority charge carriers. Minority charge carriers. So this minority charge carriers will be attracted by this positive charge. Okay. So and these electrons, what are the minority charge carriers here? The minority charge carriers in N region are holes. So they will also be attracted. So the minority charge carriers in P region, what are the minority charge carriers, sir? The electrons. They will be attracted by this positive charge. By this positive charge. By this positive charge. Of course, the electrons in the N region will be repelled by this E, but okay, that's okay. But this positive charge will try to attract the electrons from the P region. Similarly, these negative charges will be attracted, electrons will be attracted by the this negative charge here. So now what happens, sir? So what happens is there exists, so the minority charge carriers, the minority charge carriers in P are what are the minority charge carriers? Are electrons attracted by positive ions. Then so it is because of electric field. So what I can say, there exists drift current. Yes or no? The current which is existing because of the electric field. The current which is existing because of the electric field is called drift current now. Drift current. So similarly, the minority charge carriers in N region are also. So what are the minority charge carriers? The minority charge carriers in N are holes attracted by negative ions. So now if you go back and see, now the electrons are moving in this direction. So the electrons are moving in this direction. So if you want me to draw, I try to draw again. So just to make you to understand this, I am trying to do all these things, sir. Why an open circuited PN junction is electrically neutral? That is very important point for a student to remember. Many students don't even know why all these things are happening. Many students don't even know. Students like Vasu will get benefit out of it because you are just in second year. This will help you to build your knowledge very well. I'm just trying to explain you, even a drift current also exists in an open circuited PN junction diode, PN junction. So I'm just trying to make you to understand that I'm just trying to make you to understand that. So now what happens, sir, as I told you, the electrons, the minority charge carriers, that is electrons, are moving in this direction. Electrons are moving in direction. So the corresponding drift current will be in this direction. So can I call this is JN drift, JN drift in this direction. Similarly, the minority charge carriers, what are the minor charge carriers? Holes. Holes will move in this direction. Holes is moving in this direction. So what is the corresponding current? So this is nothing but JP drift. JP drift. JP drift. JP drift current. So total current is nothing but J diffusion plus J drift. This is going to be 0. Why 0, sir? Why 0, sir? Because diffusion current is in this direction and drift current is in this direction. So the total current in an open circuited junction is 0. So what can I say? What can I say is a PN junction is electrically neutral. A PN junction is electrically neutral. This point you need to remember, sir. Very important point. This point you need to be remembered. Electrically neutral. Open circuited. A open circuited PN junction. Open circuited PN junction is electrically neutral because of this diffusion and drift. So you may get a doubt, sir. When diffusion is existing, you can measure some voltage, you can measure some current. No, because this diffusion is compensated by drift. This diffusion is compensated by drift. Why drift is existing? Because you have some electric field inside. Because some electric field is inside. So if you want to try to measure, do you think if you go and measure, if you take a diode or a PN junction and connect it to a voltmeter, do you think voltage will exist? No. Why, sir? Because so it is current is neutral, electrically neutral. Balaji, it is very simple, Balaji. What I am trying to say is, for open circuited PN junction is electrical neutral because inside, as I told you, so now what's happening here is, let me tell you something quickly. So you have, before formation of this junction, what happens, sir? The charge carriers are moving from this region to this region. Yes or no? So are we applying any external voltage? No, we are not applying any external voltage, right? So, but when charge carriers are moving from one region to other region, we say that there's some current exists, and this current is because of diffusion. So that current I am calling it as a diffusion current, J diffusion, which is summation of JP diffusion and JN diffusion, right? So now because of this, now what happens, sir? Some electric field is existing because you have positive and negative ions, positive and negative ions, positive and negative ions, which doesn't have any charge carriers. So when this complete positive charges and this complete negative charges are existing across the junction, there exists an electric field. There exists an electric field, and the direction of the electric field is like this because when you put a positive ion at the center, it will be repelled and it will move towards the right side. If you put a negative ion, it will move towards the left. So positive ion is moving in this direction. Some positive charge is moving in this direction. So because of that, we are saying electric field is in this direction. Electric field is in this direction. When the electric field is in this direction, when the electric field is direction, the minority charge carriers in P region. The minority charge carriers in P region. What are the minority charge carriers? Electrons. This will be attracted by this positive charge. Right? So they will be attracted by positive charge. Similarly, the minority charge carriers in N region or holes, they will be attracted by this negative region, negative charges. Negative charges. So now what happens, sir? There exists another current called drift current. So when these are moving, when these are also moving, so what happens, sir? There exists a current called drift current, and electrons are moving in this direction, and positive charges are moving in this direction. So the charge, so you can see here the electrons are moving in this J and drift. This is JP drift. JP drift. So the total drift current. So diffusion current is moving in this direction. Drift current is in this moving in this direction. So which makes the PN junction electrically neutral. Which makes the PN junction electrically neutral. Which makes the electrical junction the PN junction electrically neutral. Clear? Okay. Now we will see what is contact potential. We'll see what is contact potential. Contact potential indicates the amount of voltage to be applied across the PN junction to restart the flow of electrons and holes across the junction. So now what happens, sir? Just 1 second. Now what happens, you can see here. What happened, you can see here. So contact potential. So what do you mean by contact potential? Contact potential. The amount of voltage to be applied, this is applied, sorry. This is applied across the PN junction to restart the flow of electrons and holes across junction. Now what happened earlier? Because of this depletion region, these charge carriers are not moving much. See, even though that, as I told you, drift is existing, that will not make much difference. Right? Drift and diffusion, both of them will be closed. So now what happens at the center? Depletion region is existing. So the charge carriers from one side to other side, if they want to move, they have to jump this. Wall kind of thing. So they have to cross this region. So the external element of, so the external voltage which is required to be applied so that the charge carriers from one region can jump to the other region is nothing but contact potential. So that means the flow of electrons and holes will happen across the junction. The contact potential is also called junction potential, the other name, or built-in potential. It can be called as a built-in potential, barrier potential, diffusion potential. Why it's called diffusion potential, sir? This potential is existing because of the diffusion process. So why these potentials occurred, sir? Is the potential is because of the electric field formed. Okay, in the derivation we will try to make you to understand. What is this? So the barrier potential is expressed in volts, obviously, because it is because of E. So its value is called a height of the barrier. height of the barrier, and it is denoted by V naught VB. Generally, barrier potential is called VB. General potential or VB we call. Generally, we call it as a VB. VB we call it as VB we call it as. So now we'll try to understand in detail. The magnitude of the barrier potential varies with the doping levels and temperature. See, which is very important. The magnitude of the barrier potential varies with doping levels and temperature. If the temperature is increasing, what happens, sir? The temperature increases, barrier potential decreases. We will discuss in detail what happens to the barrier potential. What happens to the barrier potential when temperature increased? That we call temperature dependency of the barrier potential. But just remember, the magnitude of the value of the barrier potential varies with doping levels, right? How much doping is happening? How much doping is happening? Based on that, you can define. The potential barrier can be increased or decreased by applying external voltage. Okay, so this is also an important point. The barrier potential is approximately 0.7 volts for silicon and 0.3 volts for germanium at 25 degrees centigrade. At 25 degrees centigrade. So this is important. So barrier potential for silicon is 0.7. So this is very much important. You should remember. You should remember that 0.3 volts is for germanium. Germanium. Now, the barrier potential of the PN junction mainly depends on the following factors: the type of semiconductor used. I mean, it is whether it is silicon or germanium or any other thing. Gallium arsenide. Like this is also semiconductor that we will discuss later. The concentration of the acceptor impedance P on P side, the concentration of donor impedance on N side, the intrinsic concentration, that is Ni, and the temperature. The temperature. We'll discuss in detail about this. Now, let's consider again. Let's consider again. Every time I have to draw this because this is important. Without this, we don't understand anything. This is most important. For anybody to understand the potential. That is the reason why I am trying to draw it again and again. Minus, plus, minus, plus, minus, plus, plus electron, plus electron, plus electron, plus electron, plus electron, plus electron, electron. On this side, what we will have, sir? Holes, yes or no? As I am writing very fastly, it is not coming neatly, don't worry. But understand the concept, sir, very important. So this region, what I called, sir? This region is called a depletion region. Depletion region. And this is having a length of W. And we have considered this x is equal to 0. And this point is going to be xp naught. This point is going to be xn naught. And the direction of electric field is in this direction. Now we will try to calculate. What is the value of the contact potential or barrier potential. We'll try to calculate what is the value of the contact potential or barrier potential. Now consider. Now we'll do it for holes now first. So see, if you calculate for holes, you will easily understand for electrons, right? So we know that Jp diffusion plus JP drift is going to be 0. JP diffusion plus JP drift is going to be 0. So what is diffusion? What is diffusion, sir? How will you write diffusion? It's going to be minus Q dP and then dP by dx plus drift value. How will you write, sir? It will be P Q mu P into the electric field which you have applied. The internal electric field which is existing. Right? Internal field which is existing. So what is dP here? Diffusion coefficient, and this is change in the hole concentration with respect to change in distance. Q you already know. P is nothing but number of holes. Q mu P is the mobility. E is the electric field existing. So now what I'll try to do is I'll try to make it PQ mu PE. PQ. I'll from here I'll start so that you can see. Yeah, you're able to see it, right? I think still you can, I can write from here also. So PQ mu P into E is equal to Q dP into dP by dx. Acha, this QQ will get cancelled. This QQ will get cancelled. This Q and Q will get cancelled. So what will be remaining? So what will be remaining, sir? P mu P into E is equal to dP into dP by dx. So I want to bring dx this side so that what happens, E dx is equal to dP by P into 1 by mu P, or I can write like this, dP by mu P into 1 by P into dP. Right? So what is dP by mu P, sir? dP by mu P from Einstein relationship. From Einstein's relationship from Einstein relationship, dP by mu P is nothing but Vt, volt equivalent temperature. So I can write E dx is equal to Vt into 1 by P dP. 1 by P dP. E dx is equal to Vt into 1 by P dP. Right? So can I do one thing? Can I integrate on both sides? Integrate on both sides. So integration of E dx is equal to Vt into integration of 1 by P dP. Integration of 1 by P dP. Integration of 1 by P dP. Sir, how it is looking? What do you mean by integration of E dx? Integration of E dx, did you get something? Is it not the potential? So what do you mean by potential? Sir? This is nothing but potential. Integration of. So how? Simply, I'll just try to tell you again. What do you mean by potential? So let's say you have a point A here have a point B here. You're trying to move a you're trying to move a point uh, from A to B in opposite to the electric field. The work done to move a charge carrier from A to B against to the electric field. Against electric field is nothing but potential. Against electric field is nothing but potential. So what is that? So VBA is equal to minus of integration of from A to B EDX. EDX. Okay. We are trying to move. We are trying to move. So what I can write, sir? What I can write here? So can I write this? I don't have a minus here. So I'll add and remove the minus here. So this is going to be EDX is equal to D. No, here's the DP has gone, right? So VT into integral of 1 by P dP. 1 by P dP. Now I need limits. I need limits. So how will you calculate limits? How will you calculate limits for it? So from where to where we are moving? From where to where moving? You just see. So from sorry, I did not do this. Huh? So from here to here you are moving. Oh. This is minus x naught. This is minus xn naught. Okay. So you are trying to move. You are trying to move from here to here. Sir, at this point, what exists, sir? At this point, what will exist, sir? What will exist, sir? So we are talking about minority charge carriers. We are talking about minority charge carriers or that holes. We are talking about holes. So at here, at x is equal to minus xp naught, what is the p value? P is nothing but pp. That is p is equal to pp. What is p? Charge carriers, holes. We're talking about only holes. We're not talking about anything. We're talking about holes. So this nothing but P is equal to P is equal to P is equal to PP. So at x is equal to minus xn naught and sorry P is equal to Pn, that is holes in the n region, holes in the n region, holes in the n region. Holes at x is equal to xn naught, at x is equal to xn naught, p is equal to pn. So the limits for x is nothing but minus xp naught to xn naught. The limits for p nothing but pp to pn. So if you go back and see here, so the limits is going to be what? So this is going to be minus of limits is going to be minus xp naught to the xn naught e dx is equal to Vt into, so this is what? This is what? Pp to Pn dP. This is what the limits. So Pp to Pn, Pp to Pn. So can I say this is, Vb, barrier potential Vb, yes or no? So this is going to be minus Vb is equal to Vt into, acha 1 by P is there, na? Sorry, 1 by P dP, 1 by P dP. This is nothing but natural logarithm of P with the limits Pp to Pn, Pp to Pn. So minus Vb is equal to Vt into natural logarithm of Pn by Pp. I can write, right? Pn by Pp. PN by PP. So if I want to bring that VB is equal to clear like that minus VT into natural logarithm of Pn by Pp. So this VB can be written as VB is equal to VT into ln of Pp by Pn. Pp by Pn. Pp by Pn. This is the expression for barrier potential. This is the expression for barrier potential. Important to be remembered. Many times the problems are asked. Based on this. Simply, so VB, the barrier potential. VB is nothing but barrier potential. VB is equal to VT into ln of PP by Pn. VP into PP by Pn. But what we know, sir, we know that PP is equal to ND. PP is equal to ND. Right? What is PN? PN, what is Ni square by Na? Yes or no? PP. So now if you substitute both of them here, the barrier potential VB is equal to VT into logarithm of what we have PP. PP is nothing but ND by Na square by Na. Na square by Na. So barrier potential VB is equal to VT into natural logarithm of ND Na by Ni square. This is also another important formula. To be remembered. Very important. Very, very important. Many questions will be asked based on this, sir. Many questions will be asked based on this. So VB is equal to VT into natural logarithm of NDNA by NA square. NDNA by NA square. Very, very important formula. So simply he may ask you all these things. So this is a very important formula. NDNA by NA square. So barrier potential. So what will be for electrons? If you want to know for this is for what? This is for what? This is for what, sir? This is for holes which we have calculated. Yes or no? What our short discussion. So this is for holes we have calculated. So what would be for electrons? For electrons, VB is going to be VT into natural logarithm of NN by NP. Do you need to think about this? No, it's very simple. Very simple. Barrier potential for this is barrier potential for holes. Barrier potential. So I should write here. Barrier potential for electrons. This is barrier potential for. So definitely one question is expected from this, sir. So if you are listening to my class today, you two marks is in your pocket. 2 marks in your pocket for potential for holes. potential for holes. So then again, for here also I should write this thing. Continuation to this. So what we did in the previous case. So we know that here also for n type, Nn is equal to what, sir? Here a small mistake happened. You did not tell me. This is Na. This is Nd. This is Na. This is Nd. Of course, the final answer is same. Final answer is same, but we should have the clarity, right? So this is the problem. If I teach continuously, this is the problem. Okay. Nn is going to be donor concentration Nd, and Np is going to be simply Na square by Na. Na. So this Vb is again, Vb is going to be Vt into ln of Nd by Na square by Na. So again you will get Vb, the barrier potential Vb is going to be Vt into natural logarithm of Nd Na by Na square. This is the formula same or not? Is the formula same or not? If you see, look at here. Is the formula same or not? Yes, the formula will be same almost. You will have some formula. So barrier potential will be same. So Vt into ln of Nd Na by Na square. Nd Na by Na square. So some important note, if somebody is asking you to calculate, let's say, express Pn in terms of, so if he gives you some voltage and gives you some concentration Pn, he will not give you this thing. So from that, what we can say here, so from this formula, this is some node kind of thing or some formula. So we know that Vt is equal to, Vb is equal to Vt into natural logarithm of Pp by Pn. Pp by Pn. Can I write this is going to be Vb by Vt is equal to ln of Pp by Pn. So from this, can I write Pp is equal to Pn into. So why I am writing all these things? Why I am writing all these things? Pp by Pn is equal to e power Vb by Vt. So Pp is equal to Pn into e power Vb by Vt. If you want to write Vt in terms of Kt by 2, you can write it again. You can simply write, you can simply write Pp is equal to Pn of e power, this is a Vb by Kt by Q. So you can write Pp is equal to Pn into e power Kvb by, sorry, Q, QVB by KT, QVB by KT, QVB by KT. This is important formula. Similarly, what will happen, sir? If you want to write, you can write for NN. You can write for NN. NN is equal to NP into E power Q into VB by KT. VB by KT. NN is equal to NP into E power. These are two important formulas, sir. Many a times problems may be asked, direct formulas. All these things you may not remember, but at least you should remember this formula. If you remember this formula, you will get everything, sir. What is the formula? VB is equal to the barrier potential VB is equal to VT into the barrier potential VB is equal to VT into natural logarithm of PP by PN. PP by PN. If you remember this, you can calculate this. That is nothing but ND by NS square. ND by NS square. Or he can give you PP into PN, whatever he can give. No, otherwise he may be asking this. So he may be giving this PN, VB, KT and Q and everything. So he may be asking you to calculate the PP. Or you can also calculate, he can also ask you to calculate PP or NN. So whatever. So he may ask whatever he want. He may ask whatever he want. So this is very important concept to be remembered. This is very important concept to be remembered. So one important thing from these two, can I write it here? New page I'll write. So we know that PP by PN is equal to E power Q VB by KT. At the same time, NN by NP is equal to E power Q VB by KT. Is both 1 and 2 are same or not? Is both 1 and 2 are same or not? So now you can equate them. So PP by PN is equal to NN by NP. So can I write PPNP is equal to NNPN. NNPN. So what it says there? What it says? Is it not mass action law? Can you simply write NA square? This is nothing but mass action law. Mass action law. Very important. This is nothing but mass action law. This is nothing but mass action. This also very important. So this is also very important. So if somebody asks you to calculate how we got this 0.7 volt, 0 point something. So what we know? What we know, sir? Contact potential for silicon germanium. Shall I calculate? Shall we calculate contact potential for silicon and germanium? We will see contact potential for silicon and germanium. Contact potential for silicon and germanium. So what we know? V naught is equal to Vt into natural logarithm of Nd Na by Ni square. Ni square. So for silicon, what is Ni here? Ni value we know that 1.5 into 10 to the power of 10. 1.5 into 10 to the power. Many times we have discussed. And then assume Na and Nd, both of them are equal to 10 to the power of 16 per centimeter cube. Is also there per centimeter cube. And Vt is equal to Vt is equal to, let's assume it's going to be 26 millivolts. 26 millivolts. 26 millivolts. Then what you will get, sir? So V naught is equal to 26 into 10 to the power of minus 3 into natural logarithm of NdNa. So 10 to the power of 16 into 10 to the power of 16 by 1.5 into 10 to the power of 10 whole square. So what you will get, sir? This is VB, actually VB, barrier potential VB I am talking about. So VB is going to be 26 into 10 to the power of minus 3 into natural logarithm of 10 to the power of 32 by 1.5, 2.25 into 10 to the power of 20. So almost we'll get VB is equal to 0.7 volts. 0.7 volts, what you will get? This is the barrier potential. This is the barrier potential. This is the barrier potential for silicon. Similarly for germanium, VB is going to be, I will get, but for germanium, for germanium, so for germanium, Ni, what we know, sir, Ni is going to be 2.5 into 10 to the power of 15 per centimeter cube. 2.5 into 10 to the power of 15, 16 centimeter cube. Sorry, this is 13. 10 to the power of 13 centimeter cube. So what you'll get, sir? VB for germanium, you'll get as 0.3 volts. You get it as a 0.3 volts. VB is going to be 0.3 volts for germanium. For germanium, this is the value. This is the value. This is the value. So VB for silicon is going to be 0.7 volts. VB for germanium is going to be 0.3 volts. VB for 0.3 volts. So this is what all about barrier potential. Barrier potential. Correct, Vasu. If we assume that the Na and Nd values are different, you will get the value. But at the given temperature, what is the temperature? Say at room temperature when 300 degrees Kelvin. Kelvin. If Na is increasing, Nd will decrease. So almost that is the reason why N into P is equal to Na square, right? N into P is equal to Na square. So intrinsic concentration will not change. Very good point. Good point you asked. Vasu. So you are asking that this Na and Nd will be different, right? If you consider Na and Nd, if N is high, Nd will be different, less than. If Nd is high, Na will be different. But almost the multiplication will come in the same way. That is why we consider almost this one. Okay, your doubt is correct. But if Na is increasing, if Na is increasing, Nd will decrease. If Nd is increasing, Na will decrease. If acceptor concentration is high, the diffusion concentration will be less. If the diffusion concentration is high, acceptor concentration will low. Fine, is it fine? Did you understand? And at the temperature, at Vt is equal to, at room temperature, generally, at room temperature, this is nothing but at room temperature. At room temperature, generally, we call it as at room temperature. At room temperature. At room temperature. At room temperature. Yes, that's why N into P is equal to Na square, right? N into P is equal to Na square. Oh, sorry, you may not see this. Balaji, that is what I'm saying. From mass action law, what is mass action law is saying? This is what, right? N into P. N into P is equal to N square. 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 For a given temperature. For a given temperature. Is that okay? Did you understand, Balaji? You okay? Okay. We'll move on. So we will see some applications of diodes, and then we will see actually a PN junction at equilibrium. The PN junction at equilibrium tomorrow we'll see. But before that, we will try to discuss about this very important concept called PN junction diode applications. Actually, before talking about diode, I moved forward. I moved forward very much, but this is not supposed to be discussed here. But still, so what are the different places where we can use this PN junction diode? So a PN junction diode can be used as a rectifier. It can be used as DC power supplies. In DC power supplies. So what do you mean rectifier? Did you ever see the rectifier? Did you ever use the rectifier? Have you ever used the rectifier? Have you ever used the rectifier? Do you know? Have you ever used rectifier? Sir, you use the rectifier every day. You use the rectifier every day. Where, sir? In your mobile adapter. This rectifier is present in your mobile adapter. Yes, mobile chargers. Correct, 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 correct. So in DC power supplies, so these rectifiers are used. And the switch in digital logic circuits, it PN junction diode acts as a switch. It acts as a switch, and it can be used in a clamping network. It can be used in clamping network, and called as a DC restorer. That we will discuss. We will this comes under actually an alloy electronic circuit. I have already discussed in an Unacademy app. What is the clamping network? What is the clipping network? Everything I have discussed. Everything I have discussed in detail in Unacademy app. In detail in Unacademy app. In detail in Unacademy app. Right? And demodulation detector circuits. Demodulation detector circuits. Demodulation detector circuits. And detectors in optical communications you can use. Xenon diode as a voltage regulators you can use. Varactor diode. This is very important. This is very important. Varactor diode, one of the good applications, so which is used in radio and TV receivers. So Varactor means variable resistor diodes, variable resistor diodes or variable capacitor diodes. We will discuss about Varactor later, right? And LEDs in digital systems, digital displays. We will also discuss about LED in our EDC subject. Laser diodes, laser diodes in optical communications we use. And tunnel diodes we use. Tunnel diodes are the relaxation oscillator at microwave frequencies. Microwave frequencies. Right. So in the next class, we will try to discuss in detail what is actually a PN junction. The PN junction. The PN junction at equilibrium. We will still move forward. We have calculated. Now we will just go back and see what we have discussed. What we have discussed. Just let me spend 5 minutes on this. We started our discussion about PN junction diode, how the PN junction is formed, how the PN junction is formed. So on one side of the crystal, you are pouring acceptor ions. On the other side, you are pouring donor atoms. Because of that, what happens is there exists some junction called PN junction. It is called PN junction. It is called PN junction. Then, when the PN junction is formed, These are positive ions and these are the negative ions. These are negative ions, these are positive ions. So what do you mean by positive ion? Well, how the positive ion forms, that we have also discussed here. So this is how the positive ion forms. By donating one electron, it becomes a positive ion. By accepting one electron, it becomes an acceptor ion, negative ion. This becomes a negative ion. This becomes a positive ion. Okay. So now slowly what happens, sir? So here what is happening, sir? At the junction, movement of charge carriers will happen because of the gradient. On one side you have maximum number of holes, on the other side you will have maximum number of electrons. So they will obviously, when the charge carriers are available, they will not sit properly. They will try to move from one place to other place. They will move from one place to other place. From here to here, they are trying to move. From P to N, holes will move. From N to P, electrons will move. Okay. When charge carriers are moving now, what happens, sir? This region will be depleted. Means the electrons in the N region, when they cross the junction, they will find their corresponding holes. So here what happens, sir? Electron hole recombination is happening. So from here, let's say some hole is moving from here to here. So here also what's happening, sir? The hole is moving from P to N. Again, electron hole recombination is happening. So when both of them are, now what happens, sir? There exists a potential or depletion region or space charge region or uncovered charges. These are all uncovered charges. And this region is called depletion region. Depletion region can also be called as space charge region and transition region. And now we discuss what is open circuited PN junction. So this, now we assume that x is equal to 0 here, and it's going to be x is equal to xn naught, and p, and the depletion, the penetration into n side is nothing but xn naught. The penetration into p region is nothing but xp naught. It is xp naught. So now, so W is equal to xn naught plus xp naught is nothing but width of, this is nothing but width of potential barrier, or width of the barrier, we can simply say. Width of the barrier, we can say. Opposite a potential barrier only. Width of the barrier, we can say. So what happens, sir? So when because of the gradient, when it is open circuit PN junction means because of the gradient, the charge carriers are moving because of the diffusion. So when electrons are moving from this region to this region, the direction of the diffusion will be in this direction, and diffusion due to holes will be in this direction. So there exists the something called J diffusion is because of JP diffusion and JN diffusion. Now, as the electric field is existing, why electric field exists, sir? Electric field exists because the charge carriers are, this is positive charges you have completely here, negative charges are separated. Negative charges and positive charges are separated. So now, because of that, electric field is existing. So the direction of the electric field is always from this region. So how can you say that this is the direction? You bring put one some, so let's say you are putting one positive charge. So positive charge is moving from right to left. The positive charge are moving. So the direction of the movement of the positive charge is nothing but the electric field, right? Direction of the, so this is what the electric field is. In the opposite direction you will have the electron movement. So so now what happens, sir? So now this is about diffusion, but there is something called drift. What drift current, sir? Drift current exists because of what? Drift current is because of the minority charge carriers present in the P region and N region. Minority charge carriers present in the P region and N region. Is it clear? Minority charge carriers present in the P region and N region. What are the minority charge carriers present in the P region? Electrons. These electrons will be attracted by these positive charges. Electrons will be attracted by the positive charges. The holes will be attracted by the negative charges. So this is because of something electric field. So this is called drift current. So drift current. So drift current I can solve. So the total current is going to be J diffusion plus J drift, which is equal to 0. Why, sir? So diffusion in this direction, drift is in this direction. Diffusion in this direction and drift is in this direction. So both of them are opposite direction. So because of that, the open circuited PN junction is electrically neutral. The open circuited PN junction is electrically neutral. Now we have got something called contact potential, or so that's the same called built-in potential, barrier potential, diffusion potential, right? The minimum amount of voltage which is required to start flow of electrons and holes across the junction is called contact potential. So what would be the value? It is represented with V naught or VB. V naught or VB. For my convenience, I have taken VB. So how will you? So how to calculate? That will take it later. So we will consider this. We will start. We have calculated for holes. So we have discussed in detail. We have discussed in detail how to get it. So VB is going to be the barrier potential. VB is equal to VT into ln of PP by PN. This is the formula which we got. This is the formula which we got. So PP is nothing but acceptor concentration. PN is nothing but N square by ND. So if substitute both of them, what will get, sir? VB is going to be VT into ln of ND NA by N square. If for electrons, VB is going to be VT into ln of NN by NP. Yes, yes, yes. Yes, correct, Balaji, correct, Balaji, correct. So VB is equal to VT into ln of ND NA by N square. So for both of them, potential is same. For both of them. So if this is the wall, it doesn't matter from which side you are. Yes or no? From doesn't matter which side you are. So if you want to jump from this side, let's say this is 6 feet wall. If this is 6 feet wall, you are standing to the right side of the wall. You have directly you have to jump 6 feet only, right? If you are standing here on the left side, for that also you need what? Same potential or not? Same potential energy you need. Yes or no? So the VB for both electrons and holes is same. Electrons and holes is same. Electrons and holes is same, but the only thing is direction will change. So direction is from holes, it is from P to N, and for electrons it is from N to P. For electrons it is from N to P. That's it. That's it. Nothing will change. Nothing will change. So, but they are in opposite direction. But they are in the opposite direction. So, and we have calculated something different also, PP and NP, whatever we have discussed. So, and this is our mass action law. From that we have derived, and we have calculated what would be the contact potentials of silicon germanium. For silicon it is going to be 0.7 volts, germanium is going to be 0.3 volts. And we have discussed some PN junction diode applications. And tomorrow we will discuss in detail about PN junction equilibrium. Still we have not completed, we will discuss it tomorrow. So the notes which we are discussing here, I will post it in the group, Telegram group. This is a Telegram group. This is a Telegram group. Unacademy GATE Telugu. Unacademy GATE Telugu. Unacademy GATE Telugu. Sir, in Unacademy GATE Telugu, this is a Telegram channel. You will find everything. So join that. Sir, you can find this is the number of channels. This is a different number of channels which are available. So you can go through this Creatrix GATE ECE IN, and you can have another channel called Unacademy GATE PIXE. ME, this is for mechanical engineers, not for ECE and EEE. NA, NP, NN. No, that is NA is not okay. I'll come here. So Balaji, this NA is acceptor concentration. Acceptor concentration. NP is number of electrons in P region. Then what you asked? You have N. Okay. Number of electrons in N region. Understand, Balaji? Na is acceptor concentration. Na, capital Na. There is nothing so small n. Did I ever use small Na? Anywhere? I have never used, right? This capital Na. Similarly, what is PP? Or N-type or this is a N-type semiconductor, I can say N-type semiconductor, N-type, P-type semiconductor, P-type semiconductor. PP is number of holes in P-type semiconductor. What is PN? It is number of holes in N region. Always remember, let's say NP. So this represents charge carrier. And this represents type of semiconductor. This is called subscript. Subscript, Balaji. Subscript. Okay, always remember the subscript. Always remember type of semiconductor. Don't get confused. Subscript, always remember type of semiconductor. Okay. Similarly, if you want here ND, if you are here ND, this is donor concentration. Donor concentration. Donor concentration. Okay, thank you, Balaji. So I am here for you. I'm here for all of you. I'm teaching all of you for all of you. So it is my duty to explain for you. Need not worry, right? This is a Telegram channel where I'm going to post all the notes now, and you have other channels also: Unacademy, GATE, Civil Engineering, Engineering Pathshala, Engineering Computer Science, Unacademy, GATE questions in Unacademy Telugu. So in Unacademy Telugu, if we have other class also going on, you can see, you can have math classes are going on. You can have a digital signals process, digital classes are going on. You can have communication classes, communication classes are going on. In everything, sir. In all other channels also, you have all subjects. So you can also see all these things, right? Math, digital, communications, all the subjects are going on. All subjects are going on. Okay. And you have something called electrical junction. Electrical junction for electrical people. Electrical junction for electrical people. Okay, sir. If you have time, you can also see this maths, digital, and communications. So as you are in second year, as Vasu, this will be very much useful for you even for future, right? Spend 2 to 3 hours every day from now. You will be all India first rank. It is my. Of course, the number of us doesn't make any difference, but you should practice whatever you're studying. So let's say you're in second year, right? You are second year, right? So if you're in second year, what are the subjects in your semester, right semester? Finish those subjects in GATE. That is more than sufficient. So by the end of third year itself, by the end of 3-1 itself, mostly all subjects will be finished except VLSI. That you can learn from YouTube classes. So we'll have a definitely a bright future. Clear, Vasu. Okay. So thank you Thank you for attending the class. Don't miss my tomorrow's class. So like, share, subscribe the channel, and bell icon. Hit the bell icon. Hit the bell icon for notifications. Okay. Good night. Good night. Good night for all of you. We'll meet you again tomorrow. We'll meet you again tomorrow. Thank you. Thank you.